Here we have the Matlab program where we are solving the numerical analysis and numerical implementation to solve the heat diffusion in a one-dimensional wire. And we are going to apply here the forward time center of the space method. Actually, the structure of the program is pretty much more or less the same, I would say, than the previously considered for the advection equation. There are some differences, of course, peculiarities associated to the different equation, different implementation, and different boundary conditions, and so on. But more or less, the structure, the basic structure is pretty much the same. So first, we are going to define here some parameters in order to define the heat equation and the range in space and time that we're going to consider. So here we have the conductivity, which is the D parameter we're using in theory. It's going to be here 1/2. Then we have the maximum length of the wire. Here, length of the wire. Then we have the total maximum time we are going to consider. In this case, they both are going to be 1, and of course we can change them. And then we have some parameters that we need in order to solve the equation within the explicit method. First, we have the number of time steps. In this case, we have considered 2,500. We define actually the time step, which is the maximum time here, 1 over nt. Then we have the number of space steps. Here we have considered 50, which defines the space step, which is the maximum length over the number of space steps. Then we have the beta parameter, which arises in the implementation of the numerical method, which is 2 times the conductivity times delta t over the square of delta x. And it's important to remember that as we have shown, this method actually is stable if this parameter is lower or equal than 1. So here, in order to see if this is the case or not, I'm just writing this comment here in order to see the value, to check the value of the B parameter. And actually have choosing these parameters nt and x in order to the B parameter for this case to be equal to 1, which is like we are in order to be in the border from this to the instability. Then here we are going to define the initial conditions, and that's going to be the initial temperature of the wire. And here we have chosen to be like a sine function. So in order to define the initial conditions, again, here we're going to use this I index for the space index, and it's going to run for all the space indexes, which go from 1 to the maximum one, which is going to be nx plus 1. Just remember what I said about that we cannot have an index equal to 0, because these are going to be the index corresponding to the components of a vector, and there is no component of vector corresponding to 0 component. That's why we'll start from 1, and therefore we have to finish in the maximum one, nx plus 1. So here that will be here we have the initial condition. In this case, we have chosen to be sine pi times x. At the same time, we're also defining the x vector that, again, due to the space discretization, will take some specific values. Then we have the boundary conditions, and boundary conditions are the temperature of the wire at the boundaries. In this case, will correspond to the index 1 and nx plus 1. And we have to define that at any time. And the boundary conditions that we have chosen in this case are that a temperature of the wire is going to be 0 on both ends. So that's because, for example, the wire at both ends are connected to the ice, for example, is in contact with ice. And this initial condition, it can be like, it's like the temperature of the initial temperature of the wire. And of course, that's the initial temperature of the wire, and as the temperature on the boundaries it's 0, then you have that it will cool, the temperature of the wire will be cooling down as temperature goes. So that's what we should see, actually. So After defining the boundary conditions, which at the same time we are using that to define the time vector, then we are ready for the implementation of this explicit method. But again, here we are doing that just using two loops. One is running on time and the other one is running on the space index, and this is the method itself. And so after doing that, we have defined all the values of the u function, in this case the temperature, in all the domains we have defined before. And now we are ready to show the results. In this case, we are going to show them in two figures. This one, we are plotting the temperature at different times. So these are the times we have chosen. Here we have chosen the initial time, then the time corresponding to that index, to this other one, and then the final time will be this one. And we'll be using different type of lines and different colors. Okay, then it's the title, and this is the X label and the Y label. And then we are showing another figure. Another figure in this figure it will be like it's a three-dimensional plot where in the z-axis we're showing the temperature, and here we have both the x-axis and the y-axis. The x-axis will where we're showing the time, and the y-axis will show um, the position in the wire. That will be interesting to see the decaying of the temperature in the three-dimensional plot. So these are the plots we have chosen in order to see actually the results, and then we are ready for running the program and see what we have. Actually, we know more or less what should happen. That there should be a cooling down of the. Okay. So these are the results. First, we are displaying the B value. As I told you before, the B value corresponds to be 1. And these are the two figures we are showing here. So as you can see here, we have the different lines. That the green line is a temperature just a little bit later. So first, the solid blue line here is that the initial temperature of the wire. It's the sine function. Then you can see that the green dashed line here, that corresponds to a temperature a bit later. And then just much later you have this dot blue line. You can see the cooling down of the wire. And then at temperature much more later, you can see that's almost temperature is close to zero because the wire is nearly at the same temperature as the one we do have at the boundaries. So here we can also see the same thing, but here we have chosen the three-dimensional plot. You can see that this is temperature axis. This is the time axis, and this is the x-axis. So that initially at t equals 0 you have the sine function, and then if you are making cuts of this three-dimensional plot, you will have these two-dimensional plots we have here on the left of the figure. Okay, this is the result that we have gotten here for the b parameter equal to 1, and as you can see, that's the results that we're getting actually are reasonable, are the ones that we intuitively or qualitatively we might expect from this type of equations. So now we are going to consider another b parameter. We are going to choose 200, and let's take 200 and 2600. So in this case, the d time is going to be smaller. If you're making it smaller, the b parameter is going to be smaller. So we expect the system to be stable as well for smaller b. So let's see what we have here. Let's run the program again. You have a smaller b parameter. This is the one we have in this case, smaller one. So the numerical method should be stable. And this is actually as the one. Actually, the results we're getting is pretty much the same as the ones we had before, and that's a clear indication that the system is actually stable. And now we are going to do the same, but we are going to change a little bit on the other side. We are going to make the delta x to be higher. So we are taking a number of time steps. We are going to take is 2,400, and let's see what we have. So in this case, the b parameter you have is higher than 1. And as you can see here, the results are clearly really unstable. Can you see that? So actually, you can see here in the y-axis the temperature at different times. You can see this red line here, which is showing the temperature. You can see the magnitude here is huge, clear indication that this method, even though we are getting um, uh, just by a little above the limit for stability, which is 1, we're leaving, but even though going a little bit higher, you can see that the system goes crazy, and it's a clear indication that we are reaching the instability range. So I think it's so. I mean, it's very easy to see, right, that the system, in this case at least, that the method becomes unstable. Just looking at the kind of solutions that we are getting, it's quite straightforward to conclude that couldn't be real effects. That something strange is going on with the method. It's related with the instability.